Yeah, I think it's recording right now. So welcome to the ASA Winter Lecture. It's my great pleasure and honor to introduce our today's speaker, Professor Richard Davis from Columbia University for this year's ASA's Winter Lecture. Professor Davis is a Howard Levene Professor of Statistics at Columbia. He received his Ph.D. in mathematics from UC San Diego in 1979 and has held academic positions at MIT, Colorado State, Columbia, and numerous other special appointments. He's a fellow of the IMS, the ASA, and has numerous honors and recognitions from the society. For example, he was one of the former presidents of the IMS, the editor-in-chief of Bernoulli, a recipient of the Koopmans Prize for Econometric Theory, to just name a few. It's just because it's too impossible for me to provide a full list because it's too long. Professor Davis has been doing fundamental research in applied probability, time series, stochastic processes, extreme value theory, and many others. And his works have influenced generations of researchers and scholars worldwide, and have fundamentally changed the way how statistical analysis should be conducted. For example, I was influenced by his work ever since I was a graduate student, and I have been citing his works in almost all of my recent papers on tail-dependent time series. So today, Professor Davis would like to share with us his thoughts on sample splitting for assessing goodness of fit in time series. So Professor Davis, please.
Okay, thank you very much, Ting, for that very generous and nice introduction. I wasn't really expecting that, and hope I can deliver today, at least part of it. So it's quite an honor to have this opportunity to speak to the Georgia crew. I always enjoy going to Athens and to Atlanta. I think those are the only two cities actually I've been in Georgia. And I think the last time I gave a talk to the Georgia crew was sort of a joint meeting or joint gathering in Clemson. I remember this very distinctly. It seems like these two universities get together. There's some overlap between them, and it was in 2007. It was in the spring, and I remember this distinctly because I was essentially on my way to Columbia, and I didn't really know what the future was going to hold for me. So this was like 16 and a half years ago, and I've survived New York, so I'm still here, still at it, still working. Okay, so I fear that right at the outset that my title may be a little misleading. You see the title like this, and you're thinking I'm probably going to split the data, and then I'm going to use part of the data for fitting a model to that part of the data, and then use the other part of the data for checking for goodness of fit of the model to see how well the model is performing. And that's not what I'm going to do. So this is entirely different than that, but it has, I could see where one might think that's what I'm up to here. The anyone who works in time series, one of the most important but overlooked parts of the kind of time series modeling paradigm is that you'd like to check goodness of fit. And so often you have models that are generated by ID observations or input somehow, and then you get some output from that. And in one way or another, you get residuals. These are kind of proxies for the noise terms. And what you'd like to do is check the compatibility of these residuals with the assumptions that you made on the noise. So there maybe you want to check the distribution of the noise to see if that's similar to what you assumed. But often in time series, you don't make assumptions about the distribution of the noise. Often that's left unspecified, and the only real assumption you make is that the noise generating the process is ID, maybe mean zero invariant sigma squared, something of that nature. So when you look at the residuals, you want to look at maybe the autocorrelation function or other measures of dependence, and you're not so worried about the actual distribution of the residuals. And so that's what I'm going to look at today. So this goes way back. This goes back to the 60s and the 70s, and I hope that's okay, Ting. That it's a little bit dated, this topic, but it's kind of an important one. So this is circa 60s and 70s. And I think it's some interesting things that we've discovered. So before I go further, let me mention that this is joint work with a PhD student, Leon Fernandez. So let me start with a really simple example. So this is the story. This is the whole picture. I'll just do it with an example right at the opening here. And so I want to think about an AR10 model. So this is an autoregressive model of order 10. And the way that model is specified is you think about XT is a linear combination of the 10 previous lags. So it's like regressing XT on the 10 previous observations, and then you add some noise to it. And here the assumption about the noise is that it's going to be ID, mean zero, variance sigma squared. And one way to write this a little bit more compact way, it'd be just convenient to simplify the notation a bit, is you think about XT, and then you stack the phi1 through phi10, the 10 parameters in a vector, we call it bold-face phi transpose times XT minus 1. This bold XT minus 1 just corresponds to the 10 lagged variables, XT1 down to XT minus 10 plus ZT. So hopefully you can see that this equation here is derived from the one above it. Okay, and then we'll have observations. We'll have n consecutive observations from this time series model, and then we'll need to estimate this vector, this parameter phi. And let's do this using least squares. So you can think of this equation up here as just a standard regression equation. You can think of this as y, the response, and then you have x times beta. You think of phi as beta, but if you want to use the standard notation from regression. So we'll estimate phi using least squares. And it turns out it's of this form. It's like you get an X transpose X term coming in. If you think about XT minus 1 as a design matrix, so this gamma hat 10, this is just the sample covariance function of the 10 previous observations. That's XT minus 1 transpose. You sum from 11, you don't have the observations from minus 9 or minus 10 to 0. So you start at 11, and then you divide by 1 over n. So that's a sample covariance matrix of that vector. And then you have another term. This might fit in regression context. This might be y times or x transpose y. So that's what you get here. So this is kind of the standard least squares estimate. And you should stop me at any time if nothing's clear, and I'll let Ting take care of that. So the standard limit theory for phi hat is that you take phi hat minus phi naught. Phi naught is going to be the true value, say, and you multiply by square root of n, and then this converges in distribution to say q. Q is a multivariate normal. It has mean 0, and the covariance matrix is given by this gamma 10 to the minus 1, the inverse of this covariance matrix, a population covariance matrix of this vector, boldface xt minus 1, times sigma squared. This guy on the right-hand side, the covariance is sigma squared times gamma 10 to the minus 1, means it doesn't depend on sigma squared. So that's all fairly standard. Okay, so let's look at the residuals then that you compute from this model. And first, I want to think about ZT just as a function of phi. So these are going to be residuals. You'll get different residuals depending on what you put in for this estimate or for phi. So it's going to be xt minus phi transpose xt minus 1. And just as a reminder, phi, I'm putting a subscript 0 to indicate the true value of that parameter vector. So if you replace this phi with phi 0, the truth, then you get xt minus phi 0 transpose xt minus 1, which is in fact the true ID sequence that generates the process. And so this is the residuals that you get for any choice of phi. There's always a little delay when I go forward here. And so ZT hat, the typical residuals you'll get, you put in the least squares estimate for phi, you get ZT phi hat, which is xt minus phi hat transpose xt minus 1. and this is exactly what you do in regression context. I'm belaboring this because this is an important point, and it will become later. So if you write what xt is phi 0 xt minus 1 plus a zt. You put that in for xt, so the zt comes out front. And so what you'll see is that zt hat is zt, and then is offset a bit by phi hat transpose minus phi 0 transpose. So this is the kind of deviation in estimating phi 0 times previous this xt minus 1. So it's not exactly zt. It's close, but it's not exactly the same. So in particular, with the zt hats, they're not independent. They're not independent because you have this term phi hat transpose phi hat minus phi naught, and that's present in all the residuals. So there's a common factor in each of these residuals. And moreover, there's a common xt minus 1. So if you look at zt hat and zt plus 1 hat, then you'll have one includes xt minus 1 and one will include xt. And so these are very dependent. So they're not exactly independent or even uncorrelated. So there's dependence in these residuals. And this is an important point. You have this in every problem in statistics, essentially regression or whatever, because these zts are proxies for the zt hats are proxies for the zts, but they inherit some dependence based on the estimation. And in particular, zt hat, you can write it this way: it's equal to zt, and then there's an op of 1 over the square root of n term coming in times xt minus 1. And that's just because this phi hat minus phi 0 is big op of 1 over the square root of n. If you multiply this guy by the square root of n, then it converges in distribution to q. So this thing is essentially of order 1 over the square root of n times xt minus 1. It's going to 0, but not maybe as rapid as you might like. And the goodness of fit type test that we always do in time series, this is kind of the last step, but important, is you might compute the autocorrelation function of the zt hat. In compute the autocorrelation function, I'm going to do this at lag h. We'll do it for lags h equals 1, 2, and so on. You look at the covariance of the zt hats at lag h. So you have zt hat times zt plus h hat, and then you divide by the variance. I don't have a 1 over n on the outside because on the numerator denominator, because they cancel out. I'm not doing any mean correction, but you could do mean correction. That has really no bearing on what I want to say. And what we do is you plot this as a function of h. So you have this autocorrelation plot. I'll show you one of these in a moment. And then you want to check to see if compare this with the bounds plus or minus 1.96 over the square root of n. Now, if you replace these z hats here with the true noise, the zt's, then in fact these guys are asymptotically normal, mean 0, and the variance is 1 over n. And so the typical plot, these are the default plots that R and any kind of time series software produces, is plots of the autocorrelation function together with these bands, plus or minus 1.96 of the square root of n, and you check to see if they're within these bands. And if they're within their bands, you say you're happy. You say, okay, the data, looks like these residuals are compatible with the model assumptions that the data is uncorrelated or even independent. Okay, so here's what it looks like. Here's some simulated data from this AR10, and so there's the autocorrelation. Here's at lag 1. At lag 2 is really tiny. It doesn't even register. Here's lag 3 is also tiny. And then you get some bigger ones. For lags actually greater than 10, they look a little bit more reasonable. And these red dashed lines are the plus or minus 1.96 over the square root of n. And so based on looking at these plots, it says, it looks pretty good. It looks like we did a good job, fitting the model. All these autocorrelations are safely between these bands. And on the right-hand side are box plots. So what I did is I repeated this experiment 500 or 1,000 times, and then for each lag, say lag 1, I looked at a box plot of the sample correlation of lag 1 of the estimated residuals, or the fitted residuals, if you like. And it's really tiny. You see these are really tiny box plots. In fact, the plus or minus 1.96 of the square root is really not the right thing. It should be much smaller. It should be in here. I don't know if you can see the arrow on my mouse, but these levels should be. I mean, you might expect them to be somewhere in here somewhere, instead of the dash lines being way out there, at least for these guys down here. For larger legs, it looks like it's in the right spot. So something's not quite right. We shouldn't be looking at these plots. We should do some sort of correction. And this is what Box and Pierce said in 1970. So this goes back a ways. It's like 50 years or so. And they give the limit theory of the sample correlation function based on the estimated residual, and it depends on the AR coefficients. And you probably should make this correction before you declare that you have a good model fit. Maybe these guys right here are really larger than what they should be, but nobody does that. Okay, this is just people just compute these plots. The routines that coming out of like R or whatever, they don't make that correction because they don't really know the model they don't necessarily know what the model is that you fitted to the data. So these corrections are model based. So I'm going to do things a little differently. That's okay. And what I'm going to do is I want to estimate phi using the first n over 2 observations. I want to use the first half of the data set to estimate this parameter phi. And I'll call that estimate phi hat sub fn. And then I want to compute the residuals, zt hat of phi hat. So when I set up the zt's of phi, I could put any value of phi. And what I want to do is put in the value of phi hat fn based on estimating the AR coefficient based on the first half of the data. So when you do that for that same data set, we get this sort of autocorrelation plot. So the guys now at small legs, 1, 2, 3, and so on, they're not like near zero. They were virtually non-existent up to leg 6 or 7 or whatever. And now these look a little bit more reasonable, and these bands look like they may be the right sort of ones, especially for the smaller legs. Not much has changed up in the larger legs. And if you do the same thing I did on the previous slide, so I do box plots. I repeat this experiment 1,000 times. Each time I estimate the phi based on the first half of the data, and then I calculate the residuals for all the data. And then I look at the autocorrelation function of these estimated residuals at leg h. They seem to have the right distribution. There's no difference depending on the lag. There's no correction that one needs to make. So this was curious why this happened in this fashion. I was not really expecting that. Okay, are we good so far? Any question about that's kind of that's the theme here. And if you have a question, you should stop me. But hopefully I was clear. All right, we're good. I get a thumbs up. Okay, so I want to take a little deeper dive in this calculation. I just showed you pictures of what's happening, but let me go behind the scene here. So let's do a little deeper dive, and I want to do it with an AR1 model. So I was motivated by this paper by Pfister, Buhlmans, Skolkoff, and Peters in 2018. And they use sample splitting for examining residuals from a regression model. And what they did is you get the residual from a regression model, and then you might use permutation procedures to test some various properties of based on the noise. And I wanted to do exactly the same thing for a time series modeling framework. So I looked at this paper, and they did this sample splitting. So I was kind of excited. So wow, this should work for the for time series models. So, I mean, what could be different? It was key that they had a kind of a standard regression model that they had independence from one set of observations to the next. So I wanted to extend this idea in this paper to a time series models. But as I said, they were assuming independence of data. And unfortunately, this didn't work. And it kind of failed miserably. So let me show you what happens here. So let's think about just an AR1. The ARP kind of falls in it's the same setting, but a little less heavy on the notation. So xt is equal to phi xt minus 1 plus et. This is an AR1. We're going to split the data into two possibly overlapping sets. So this is a little different. Normally when people do sample splitting, there isn't any overlap in the data. You split it, maybe take 30% of the data to estimate parameters, or you take 50%, and then you hold back another 50%, but you don't confound the two. You don't contaminate one with the other. So I'm going to use the first FN set of observations, and I'm going to use that to estimate the parameter phi. So I'm going to get something called phi hat. And then I'm going to use the last ln of the data to compute the residuals. So the last ln of the data, so the zt hat is going to be the zt minus, I went through this in the AR10 case, is a little simpler. You get phi hat minus phi times xt minus 1, and it's for the last ln observation. So you go back to n minus ln plus 1, and you take that out to n. So you get the first fn, estimate the data, and then you get the last ln. And there may be overlap between these two sets of observations. I'm allowing for this. This n minus ln plus 1 might be less. The first guy that you take to compute these residuals, this guy might be less than fn. So there could be some overlap. And as this guy here could be less than fn. Now, when you look at correlations, you have to look at covariances, divide by variances. So the variances based on these residuals, and I just want to look at the last ln residuals. And it's just going to, you'll estimate the variance, you just take the sum of squares of these residuals, and I'm dividing by ln because there's only ln of them. And these guys are going to conversion probability to sigma squared. So there's nothing kind of strange about this particular term. The fact that we're estimating the ZTs, you get the same limit regardless of, you'll get sigma squared here. So this has really no impact on the estimation. It doesn't impact that sort of limit. Okay, so again, we have the first FN observations, and then we have the last LN observations. I want to look at the sample autocovariance then based on the last LN observations. So if we look at this at lag H, so that's the notation, that's gamma hat, that's this covariance. The LN means we're using using LN observations. The Z hat, that's just the estimated residuals, and this is at lag H. Square root of LN because we're using LN observations. So this is going to be square root of LN times ZT plus H. This is just the lagged values of the estimated residuals. And then you use this expression up here. So you place these ZTs with the ZT minus phi hat minus phi times xt minus 1. You do it here and you do it here. And you do the multiplication. So this is not heavy duty math or anything like this. And one term that will come out is you'll get a ZT times ZT plus H. And that will be the sample covariance function that's given by this term gamma hat ln of Z. There's no hat over the Z because these are the true noise terms that generates a process. And then when you multiply this guy, this ZT hat times ZT plus H hat, you're going to get some confounding terms or cross terms. You're going to get phi hat minus phi squared times xt minus 1 times xt plus H minus 1. And you'll get some terms multiplied by ZT. And when everything is said and done and you just retain the terms that contribute something useful, you get an expression like this. You get square root of ln divided by fn, and you'll get the sum from j equals 2 to fn of xj minus 1 zj. So you'll get a term like this, and then what's left over is going to be little op of 1. Okay, so we're going to get two terms. We're going to get this guy here, and then we're going to get this guy here. And so let's look at the limit behavior of these two guys. This term here, the xj minus 1 zj, this is a martingale difference sequence. So you're going to get a central limit theorem coming from this term here. So you're going to get asymptotic normality here, and you're going to get asymptotic normality here. This is the standard asymptotic normality for sample covariance from ID observations. So there's a joint central limit theorem that comes out of this. For the first term here, this is the sample covariance based on the true noise. That's just going to be asymptotically normal mean zero variance 1 over ln. So if I multiply by square root of ln, you're going to get a 1 up here in the upper left corner of the limit covariance matrix. For this term down here, the second term, the second component, you're going to get something called KRA times 1 minus phi squared to the minus 1. This KRA corresponds to the limiting ratio. We're going to think about ln and fn both being proportional to n, and so this KRA just corresponds to the limit ratio of those two. And then what's the cross term, the covariance, is you're going to get a KOV, which is an overlap term, times phi to the h minus 1. Phi is the parameter in the AR1 model. So this overlap is just how many observations in the first Fn and the last Ln overlap relative to Fn. So these are the number of observations that are overlapped up here, and then we're just dividing by Fn. So this is a limiting overlap. And the theorem is that when you take the square root of ln and you look at the sample correlation function, so now I'll take the covariance and divide by the corresponding variance, that this thing is asymptotically normal. It's normal, it means zero, and then you get a variance here, sigma squared gamma. And that's the thing that we're interested in. What is this variance? And you derive that from this equation, this joint convergence up here. And it turns out that the sigma squared gamma has a very nice form. At least I think it's nice. You get a 1 that corresponds to this limit of the sample covariances of the true noise. And then you get a KRA minus 2 times KOV times this function that involves the unknown parameter phi. So it comes out as the ratio KRA minus 2 times the overlap. And so if you set this thing in green equal to 0, then you get 1. You get exactly what you get for looking at the sample correlation of just the ZTs themselves. So if you take this KRA minus 2 KOV to be equal to 0, then you get the same limiting behavior, and this would be for all lags H, as though the Z hats were actually ID. So you don't have to worry about any sort of correction factors. And when do you get this equal to 0? KRA minus 2 times KOV equal to 0. Well, if you take ln equal to n, that is, you use all the residuals, which is what I did in those pictures, and then I chose Fn to be half the data set, n over 2, then this KRA, this thing is going to be equal to 2, and this overlap is going to be 1. So when this KRA is equal to 2, the K overlap is going to be 1. So this thing is equal to 0. And that's exactly what I did in those simulations. So that shows, it's supposed to demonstrate the fact that you get the same limit when you choose half the data set for estimating the parameter and use all the residuals, all n of them, for it's just half of them as well. if you take ln equals to n and fn equals to n, this is what we do now. We use all the observations to estimate the parameters, and we use all the residuals. In this case, the KRA, the ratio is equal to 1, and the overlap is equal to 1. So you get 1 minus 2, which is minus 1. And so what you'll see here is that this thing in green turns out to be minus 1, and that's the Box-Pierce result. This 1 plus this negative number here is going to give you something much smaller, and that's why those box plots were so tiny for those small legs. It's compensated by, as phi is a number between minus 1 and 1, as phi gets larger, then of course these things for larger legs goes to 0. So it's not so noticeable, but for smaller legs, it's quite noticeable. And so that's what's going on. So I think this equation kind of explains a lot. And so this difference, you'll see it coming up frequently here. So that's the deal. And so let me just show you a little bit more complete story. So this is for this AR. Let's go back to the AR10 for sample splitting. And what I'm going to do is I'm going to use ln to be equal to n. So we're going to calculate the residuals for each data point from 1 up to time n. But I'm only going to use fn of the data, so to estimate the parameter. So the ratio KRA is the limit of ln to fn. So in this case, I'm going to think about choosing multiples of 100. So I have 1,000 data points. So in this first screen here, if we use 100 data points and that k is equal to 1, we'll use the first 100 data points. And so the overlap is going to be 1, but this ratio is going to be 10 divided by 1, which is 10. And what you see in this case is that coefficient is going to be negative, is going to be positive. So what I'm showing here in these plots is the red dashed lines is the plus or minus 1.96 over the square root of n, but the black curves here are the estimated plus or minus. Well, it's essentially the 0.025 quantile, the sampling distribution, and the 0.975 quantile of the sampling distribution of the sample correlation function. So these are essentially confidence intervals. You can think of the red as confidence intervals. And the black is confidence. The red is the confidence intervals you'd like to achieve, and the black are the ones you actually get. And so what you see is that these things are really quite large for if you don't use enough observations. But as you use more observations, this black curve starts approaching the red. And at 500, it's exactly the red. That uses half the data to estimate the parameter. And if you start using more, then you see these black curves start going below the red. And then finally at 1,000, then you get the Box-Pierce result. So you see these confidence intervals get really tiny for small lags, and then they approach the red as you get for higher lags. So this kind of explains, I think, what's going on, and I think it's quite revealing. The magic is you choose half. You don't choose a third. You don't choose 2/3. You choose a half, and you get what I would view as the right-looking residuals, at least for kind of a assessment. Okay, are we good on any questions at this point? Take a little break here. Are we good, Ting? All right. So it looks a little artificial. Okay, he did it for an AR, but it's true much more generally. So the same results hold for more general models. So we can think of ZT or XT, the data following a causal and a vertical model of the following sort. You take XJ, it's some function of you inject the system with ID noise, and you think of XJ as a function of the infinite paths of these Z's. It's a shorthand notation. It involves some true parameter beta 0, and you can invert it as well. So xj is a causal function of the z's, and the zj is invertible, that you can recover the zj's from the infinite paths of the x's. So this is a lot of models fit in this sort of framework. And here we can set zj of beta. So if we replace beta 0 with some other value of the parameter beta, that's how we would get the residuals. And the idea is that you want to estimate the residuals, so you replace beta by beta hat, and that you get the zj hat of beta hat. And I'm going to do this for the last ln observations. Typically, I want to do this for all n observations, and then I'll estimate beta based on the first fn observations. And we need some assumptions on the G and H, essentially smoothest type assumptions. And we need to know something about the estimate that we're using for beta. So under some sort of basic assumptions about that estimate. And we have with FN is take the first half of the data and then use all the residuals. The sample correlations are asymptotically normal, mean 0, variance 1. And I should say they're also asymptotically independent at different lags. If we look at a vector of these guys from h equals 1, say up to h equals 10, those converge are asymptotically normal, ID normals, mean 0, variance 1. So that allows like a Lund box type style goodness of fit tests on not just one correlation, but a group of correlations. You could use a chi-square test. You just take the sum of squares of these sample correlations from some lag h equals 1 up to some lag k, say, and then that will converge and be asymptotically chi-square with k degrees of freedom. So that's also quite nice here. So this theorem, Armour processes, Garch processes, they kind of fit into this frame. Okay, so what I was really interested in was the auto distance correlation function. It's interesting that when you do research, what I wanted to use was this result about data splitting for auto distance correlation function, because I've been using that as a kind of a measure of dependence, especially for goodness of fit. The autocorrelation function of the residuals is just good for kind of measuring things being uncorrelated, but it doesn't work so well if you're looking at more general dependence. And so I've been using this auto distance correlation function, which is kind of an interesting idea. And now it's not so new. So if we take two p-dimensional vectors, x and y, the distance covariance between x and y, which I'll define as t of xy, what you do is you look at the joint characteristic function, that's phi xy of st, and then you subtract off the product of the two marginal characteristic functions for x and for y. And then when you're done with that, you take the modulus squared, and then you integrate this out over s and nt. And so depending on this weight function, if this weight function has support over all of RP cross R of P, then you can see that x and y are independent if and only if there's students listening on, x and y are independent if and only if the joint characteristic function factors into the product of the two, which would mean that t of xy is 0 if and only if x and y are dependent. So it's a very nice idea. It's a measure of dependence or separation from being in. And a common choice from you is this one. Selleck uses this and makes a pretty good argument in this paper and later papers, and others have also looked at this, that this is a pretty good weight function to use. It has some nice properties. It doesn't actually integrate out to something a finite. It's an infinite measure. It puts infinite mass at in the neighborhood of s and t, neighborhood of 0. But what's particularly nice about this choice of weight function is that you don't have to do the integration. You just don't want to integrate characteristic functions over RP cross RP. And so there's a nice explicit formula for this T of xy when you use this particular wave function. And so let's think about alpha equal to 1. That's what typically people use. They will take alpha equal to 1 here and here. And so what you get here is just this T of xy is explicitly the expected value of the absolute value of x minus x dot. Now, what I need here is x dot, y dot, x double dot, and y dot. There are ID copies of x and y. So there's an explicit form for this T of xy given by the expected value of the absolute kind of deviations from x with its an independent copy, and y from its independent copy, and so on. It's really quite nice. And I think if you were going to say, this is 0 if and only if x and y are independent, that it would kind of surprise you at first. But it's a nice relationship. Sometimes this form of Selke doesn't really work. In particular, it doesn't work in this regression problem. May not work in these regression problems. So you might want to use something else. And so you could use a product measure for mu. Mu1 cross mu2 is a product measure, and often people use a symmetric mu1 and mu2. And then this T of xy also has a nice form. You have to define it, or it's given in terms of the Fourier transform of these measures, mu1 and mu2. And if you choose nice ones, such as mu1 and mu2 being Gaussian, which is a nice finite measure, then this has a very explicit form, much like this guy does up here. So those are often used as well. Okay, so T of xy is going to be a population quantity. It's kind of a measure of dependence between two vectors x and y. And then what I'd like to do is be able to just realize xy to y and z. This should be xy here. So we're going to estimate t by t hat, and all you do is you replace the characteristic functions in here with the empirical characteristic functions. So we put in hats there, there, and there, and you do this integration. So these so phi hat is just the empirical joint characteristic function, and this t hat xy is a very nice form. It's just the sums of absolute deviations from x with from xi with xj and yi and yj. It's very explicit. You don't actually have to do the integration. So how do we use this for a time series setting? I want to think about the lagged distance correlation. And so this is going to be the auto distance correlation function, which I'll define to be r hat. So we'll take t hat, and now I'm going to replace x and y with a argument h, which is the lag. So we'll replace x up here, and here with xt, and then we'll replace y with xt plus h. These are both kind of univariate. And then downstairs, we'll replace it with xt and xt. Okay, so this will be just a function of a. So this is the distance correlation between observations and lag h. And then there's a result by with a couple others. Person that you may know most there is Thomas Mikosch, a longtime collaborator, and Phyllis was a Ph.D. student of mine. Tsui is a professor in Japan. And so under suitable conditions on this weight measure, it turns out that when you multiply this distance autocorrelation function by n, that this converges in distribution to this integral of chi on the integrand on the inside is a Gaussian process. It's a Gaussian, two-dimensional Gaussian, it's a random field. In other words, it's a GH of ST, and then you integrate out relative to mu, and then you have this other constant coming out from the denominator. And then we also showed that if you look at the residuals from the AR model, that you get a similar result. So we replace the z with the z hat down here. So these are the estimated residuals. That you get something like this, except this instead of this Gaussian process, there's just a bit of a distortion. You get another Gaussian process coming in, CH of ST coming in. So this is not quite the same as what we have up there. So this is the G and the CH these are two bivariate Gaussian random fields. And this is true not just from an AR model, but more general models as well. So I want to do the same thing that we did for the autocorrelation function, is look at the first Fn observations for estimating beta, and then look at the last Ln observations. Ln will typically be n, that's the hope. So we'll use all the observations to get the residuals based on this, based on beta hat Ln. It should be beta hat Fn there. And the result is, if you look at this ratio, look at R hat of Z hat Ln of H times Ln. So Ln is playing the role of n before, so you can think of Ln as being n if you like. And this converges to essentially the same thing as what we had before. We have the CH of ST, and then we get this guy down here. So the CH has a very nice form. It has some constants coming out. I don't want to bore you too much with that. The main thing is that it involves Q. This is this limit random variable for the parameter estimates. So in a sense, it's kind of a deterministic Gaussian random field. And there's some assumptions being made, whatever. I don't want to, it becomes quite involved, but there's parameters of this VHST. It's a function which corresponds to like a characteristic function. It's a lot messier than what we have for the autocorrelation function, but these things can be computed. So this guy converges to, so if we use the last Ln observations and we use the first Fn observations, this thing converges to this integral of G, the CH. And this CH is kind of an offset. This is due to the estimation in the model. And I want to know is, when is this guy in distribution exactly the same as without having this term? So suppose I get rid of that term, when is that the same? So in particular, I'd like to know, when is this guy stochastically bounded by this guy without the CH? This is what you get when you, for the true Z's, not the Z hats. When is one bounded by the other, and when are they the same, and when is this guy stochastically bigger than this? It's hard to believe that this thing could be exactly the same. I mean, this thing is not zero. So at first glance, it looks like this is impossible. This is always going to be stochastically bigger than this, but that's not quite the case. So what the implication is that if this is stochastically smaller than that, then the quantiles for this distance correlation function can be smaller than those for what we get for the Z's, for the true Z's, and if it's bigger, then these quantiles are going to be larger. And so when does this happen? So here's the thought. Let's choose sample splits so that these two processes are the same, that they're that they're equal in distribution. In fact, so that they have the same covariance function for all S and T. If that's the case, then we're in good shape. And I can write down this covariance function of this guy on the left-hand side. It involves the covariance function of the term on the right-hand side. So this thing is equal to a term here, and then something in the square brackets. If the thing in square brackets is equal to 0, then they have the same covariance function, so that you'd use the same quantiles. So just repeating that up here, and this is a mess, and I don't want you to even look at that, but just think you got square brackets. You want to show that that thing in square brackets is equal to 0. And in the case when interline process is an armor process, the thing in square brackets looks like this. You get a square bracket here, a big square bracket, and then you get times this term here. And this, you get this KRA coming in, and you get this overlap, and you get ratios of characteristic functions of the noise, the derivative, to the actual correlation function. And so what you'd like to know is, when is this thing in these big square brackets equal to 0? Now, if you take the noise to be normal, And it's a standard exercise that this ratio here is -1. So these two terms are -1. So you add -1 twice, you get -2. And so you get exactly KRA minus 2 times K overlap. This is equal to 0 when the overlap is KRA over 2. So this is exactly the same situation we had for the autocorrelation function. So for this armor process, if it's driven by a Gaussian process, you get exactly the same kind of configuration. That is, if you use the first half to estimate the parameter and then use all the data to estimate the residuals, this thing it works, and you're happy. What happens if you use a different noise? If Z is Laplace, or if it's students T with finite variance, then it turns out that these guys are this term here is greater than -1 for all T. And so that implies this term in the brackets is always positive. So that means that this covariance of this thing that with the displacement is always going to be bigger when KRA is greater than 2 times KOE. And what that means is that this limit random variable is stochastically bigger than what you get for the corresponding ID sequence. That means that the quantiles are larger than what you get in the ID case. So you have to do some sort of correction. Okay, I'm running short on time, but there's a similar expression for Garch processes and that sort of thing. Let me just show you. There's some technical things in here that's being used. So I'm sweeping a lot of stuff under the carpet, but there's a lot of technical things that go into that to show things are stochastically bigger than another. And then there's things about characteristic functions where you have to use some theory of the special functions to get these sorts of results. Let me skip this Garch one example and just go to some pictures. So here's this is the distance autocorrelation function for this AR10. I'm going to use ln is equal to n. I use all the residuals. I'll use the function of 100k times 100, and k will go from 1 to 10. And in this case, the KRA minus 2 k, it's greater than 0 for the first 5, and then it's less. And here, the distance correlation is non-negative. So this is the red is what you should use if you have ID noise. And you see if you're using the estimated residuals, they would be much bigger than what you would think if you don't use enough data to estimate the parameters. But when you use 500, they overlap perfectly. And then when you use all the data, for example, 1,000 to estimate the parameter, the level, the 9.5 confidence interval becomes much smaller than what it would be for ID sequencing. So this tracks pretty much what we had for the autocorrelation function. It gets a little bit more complicated for other distributions that you might use. This is for Laplace. It's kind of the same, but it doesn't agree at 500. And there's a similar thing for Garch, but let me just skip those. I think maybe I'm running out of time. So there's a question about, what about power? So, so maybe this gives us the right, sort of confidence intervals and much more attractive looking confidence intervals. But maybe by using just half the data, you're making a sacrifice in terms of power. If the model's not quite right, well, these things really show up. And there's a set of plots here that are a little bit complex to kind of explain in a short period of time. But the power is quite good, actually. So there doesn't seem to be any sacrifice in power. And also the size of these tests, using this, the half of the data to estimate the parameters, seems to be much better than the traditional ones based on the home box test. So it's certainly competitive. It's actually better than that in terms of the size of tests. So there seems to be no sacrifice. So there's no real downside. This maybe I should show in terms of power for one example here, this has to do with fitting AR1 when you have a Garch noise instead of ID noise. And the red corresponds to the distance auto covariance function. And what this power means that these are the auto distance correlation function is much more powerful than using tests based on correlations or the Lund test. And it's even more so the further away you get from kind of a line. So that it just shows that you should be using auto distance correlation function for some of those. I have a little postscript here, and someone brought to attention a paper by Durbin, which I don't think is well known. It's cited, but I have a feeling people cite it because other people cite it, but they don't actually read it. And they anticipate what's going in based on what's in it, based on what the other person who cited it. And there's this perpetuation here. And I don't think anyone really actually read this paper in much detail. Well, I did, because someone brought it to my attention. And it's a really interesting result. It's not well known because this is a paper that was presented at an Oberwolfach meeting in 1976. And it was reproduced in a book by Springer in 2006. But who reads books about papers given at Oberwolfach? So it's not widely known, I don't think. But it has to do with this half sample device. And what he says, essentially, if you're doing like a Kolmogorov-Smirnov type test and you use the empirical distribution function, we know if this is the true parameter that and you take Fn hat of t theta naught. So this is using the integral probability transform using the empirical minus t, that this converges to a Brownian bridge. And the question is, if you estimate theta, what happens? And if you estimate theta, you need to make a correction. And what he says, if you just use half the data to do the estimation, you don't have to make the correction. This is pretty similar to the same kind of theme that so let me bring this home. The take-home message is estimate the parameters using the first half of the data, calculate residuals based on the entire data set. The model is correct, then these correlations should have be asymptotically normal, mean zero variance 1 over n. Do what we already do. This is legitimate, and I think we should be doing this. If I had a chance to rewrite to an updated edition of Brockwell and Davis, I would do this. I kind of emphasize that we should be doing this. It's easy to compute. There's no complication in doing that. And in some cases, using the auto distance correlation function, using the same kind of data splitting, using half to estimate the parameter and using the full data for the residuals, you get the same asymptotics as you do using the true noise. And then there's more to be said about this, but that's some future work. So I hope I'm not too much over time, that you're not missing dinner or anything like that. So thank you for your attention.
Let's thank Professor Davis for the very wonderful talk. Any question? I actually have just one comment. I think Professor Davis has been very humble about apologizing for it being not very new material. Not at all, Richard. Those are important pieces of time series analysis, and we learned a lot. We really appreciate that.
I wasn't really apologizing for not being new. The topic is old, but these are new results. So.
Yeah.
Yeah. I didn't do statistical learning or high dimensional statistics or anything like that. This is just pretty classical, circa 60s, 70s.
Yeah, I think those are very important results for us. It's very fundamental. Now I have a new tool to use.
Yeah, so if you're teaching time series, you should be doing this. This is my...
Right. I actually have just one small question. So if we use the not just the half of the sample, we can do some correction So just wondering if you have any guidance about which one may be better in which situation or things like that.
I would always use that. The question might be,